Hi class. So today we're going to learn about the rate law and something called the order of reaction. So this is going to be a little bit mathy. So we're going to come up with a mathematical expression that is related to the rate of a reaction. Okay. So before we get into that, we need to talk about why reactions might be faster or slower. So we're going to talk about chemical kinetics. Okay, remember, kinetics is all about movement. The word kinetic implies movement. Okay, so we're going to talk about the movement of chemicals and how they might affect the rate of a chemical reaction. So the rate of the chemical reaction can be altered by a number of factors. Okay, the chemical nature of the reactants is important. We'll talk about what that is in a second. The temperature of the reactant, the concentration of the reactant, the surface area of the reactant, and a catalyst. Okay, so we're going to talk for a little bit about why these things might speed up or slow down a chemical reaction. So we'll start with the catalyst because the catalyst is the easiest thing. So a catalyst is a chemical that is not involved in the reaction, meaning it's not a reactant and it's not a product. Okay, so it's not involved in the actual, its atoms aren't involved in the actual chemical reaction, but its presence, right? So it's present during the chemical reaction. Its presence speeds up the chemical reaction. So for all chemical reactions, if you add a catalyst to them, it will make the reaction happen faster, right? It never slows it down. So that is number one, okay? Number two, the surface area. So the higher the surface area, the faster the reaction, right? And this is all about collisions. So I want you to think about this, okay? Let's draw a couple of beakers. Okay, inside the beaker is some sort of, oh, that didn't work very well. I was trying to draw water and it didn't work out for me. Okay, so inside the beakers, we have some sort of liquid and it's going to react with something solid, okay? So one option is a block. You can drop a block of, that's not a good looking block. I'm trying to draw with my trackpad. It's a bad idea. Let's get out the pen. Okay. So in one beaker, you have a block. This is terrible. I'm going to get this, guys. Okay. So you have two beakers. And let's say the beakers have, they're both filled with water. They're both filled with an acid. Let's say they're both filled with an acid. And I'm going to drop some metal in the acid. And the metal and the acid are going to react. Okay, it's going to be the same amount of metal, and it's going to be the same type of metal. Okay, but one is in a cube, a block, and the other is in a thin sheet. Which one do you think will react faster? The block or the sheet? So the sheet actually will react faster. The block has a low surface area. And the sheet has a high surface area. So what that means is that for two things to react, they have to come in contact with one another. So in the middle of the block, there are some atoms that are not being touched by the acid. But almost every atom in the sheet, maybe all of the atoms in the sheet, if it's very, very thin, will be in contact with the acid. Right? So the sheet with the higher surface area will happen faster than the block with the lower surface area. So this will be a fast reaction. And this will be a slow reaction. Okay, so you can think about it that way. You can also think about it. I wonder if I have a video that I can show you. There we go. Let's take a look. Oh no, I want to see the video. I need the video. Okay, I assume the video is on this page somewhere. There we go. Let's watch it on YouTube. I'm going to mute this guy. Okay, so this guy has drawn basically two pictures. This first one on the left has a block, and the other one on the right has the smaller blocks. So this could be like a sheet, or like if you have something ground into a powder, the particles are smaller. Right? So if this is a metal block, can I draw this? No, I can't. So I tried. On the left side, we imagine this is submerged in an acid. Okay, so the particles on the outside can interact with the acid particles. So the acid particles are like the whiteboard, right? The white area around it. So these four along the top, they can all react because they're all they're all on the outside. And these ones down the left side, along the bottom, and on the right side, okay? They can all react because they're on the outside. But there are four dots in the middle, and they're not touching the acid. So they're not going to be able to react. So there are 20 particles here. No, sorry, that's wrong. 1, 2, 3, 4, 5. There are 16 particles here. It says only 16 particles can react, but this guy can't count. There are 16 particles total. Only 12 of the 16 can react. Isn't it amazing how people can be smart in chemistry and dumb in counting? Okay, so this one, they're all broken into smaller particles. So you can see, right, there's space between for the acid to come in to react with the metal, right? So it can touch the two on the top and the two on the bottom of each particle. So all 16 particles can react. Man, I can't believe he put that up on YouTube and he couldn't count to 16. Okay, that's the idea. So if there's space between particles, that means it has a higher surface area, right? This block has a surface area of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 12 particles can react. This has a surface area of 20. No, again, this is sorry, this one has a surface area of 12, 12 particles can react. This has a surface area of 16, and all 16 particles can react. So what does that mean in terms of, I can't watch him in his bad counting. Okay, so what does this mean in terms of, so we have an experiment here, and we have 3 beakers, I think, of acid, and we have 3 types of substance that we're going to put into them. So let's, I don't know if you can hear this. We'll listen to this guy, even though he can't count. Let me reshare my screen. Gotta make sure we have the sound. Okay.
Each containing dilute hydrochloric acid, and these containers have got marble in them. The chemical name for marble is calcium carbonate.
So we have 3 containers. Each contains an acid, and then we have 3 forms of calcium carbonate. Okay, and normally these undergo a chemical reaction, and they produce bubbles and things like that.
Here the marble is divided up into fine powder. In this one it's relatively, well, medium-sized chips, and here there's fairly large chips of calcium carbonate.
So the larger the particles, the lower the surface area, because the larger chunk you have, the more atoms are stuck in the middle, and they won't get to react with the acid until the particles around them are gone, have reacted. So we're going to see the difference in rates of reaction. So the powder has the highest surface area, and the big chunks have the lowest surface area.
Now what we're going to do is going to put them into the dilute hydrochloric acid, and just by observing it, make a note of the rate of reaction, how fast the reaction goes. In other words, how fizzy it gets. This is the one with the large chips. As you can see, the reaction's fizzing. It's not particularly rapid, but it's going fine. And the reaction shouldn't take too long to complete. With the medium-sized chips, however, you can see the reaction's much faster. And then
So when we talk about the rate of reaction here, we can observe the rate at which the bubbles are formed, right? That's carbon dioxide gas that is a product of this reaction. And you can see we saw a little bit of bubbles formed with the big chunks, but probably the best way to observe the speed of this chemical reaction is to look for the white chunks. You can still see the white chunks. So this still has quite a lot of calcium carbonate left to react, and you can see the big chunks. Okay, the medium size, you can see it still has a little bit along the bottom, but it's already reacted more than the big chunks. So the only thing that is different is the form, right? This is the same amount of calcium carbonate in each container. So the amount hasn't changed. It's just how finely it's crushed. Okay, so this wasn't crushed into very small pieces, and you can still see the pieces left. This is medium, and then what he's going to do now is the smallest chunks. Right? So try to look at the rate at which the white stuff, the white solid stuff, disappears. I know it's not easy because the water becomes a little bit cloudy with the carbon dioxide.
I come to the powdered calcium carbonate.
So you can see quite a big difference in the amount of
Fairly obvious
bubbling.
to see that surface area, increasing the surface area, increases the rate of reaction.
Right? Much faster bubbling in the powdered version than compared to the other two. Okay, and if this guy who can't count had let the video go on for a little bit longer, as soon as the bubbles cleared up in the third container, right, you wouldn't see any calcium carbonate left. And you would still see that there's a little bit along the bottom there, and that there are quite big chunks on the third one. Okay, and if you leave these two for longer, eventually everything will react, but we can all agree this one is the winner for the fastest one. So that is, and it's probably very intuitive too, right? Powders react faster than big chunks. Concentration. Let me zoom out a little bit. Okay, so surface area, the higher the surface area, the faster the reaction because there are more collisions between actual particles. Okay, when we're talking about concentration, right? Concentration, when you have a solution, right? Because we talk about concentration with solutions, you have a solution that is a mixture of water and another particle. And it's not usually the water that's doing any reacting, it's the other particle. So if something has a high concentration, there is more of that other particle. If something has a low concentration, there is less of that particle. Right? So we talked about, when we talked about surface area, we talked about the importance of molecules being able to collide, right? To smash into each other when they react. So let's look at the idea of collisions in concentration. So we're going to pretend this is actually a gas simulator. It's not a solution simulator. Okay, but you get the same idea. Okay, so this black space is water. And I'm going to put one pump of particles in it, right? So I would call this a low concentration. Okay, so here the blue spheres represent one reactant, and then I'm going to add a different reactant. I'm going to add one pump of red spheres, and you can see that sometimes the red spheres and the blue spheres, they collide, right? So when molecules collide, they have a chance to react. These ones are not reacting, but you can see them bounce into each other. Okay, so the more they collide, the more they bump into each other, the more likely they are to react. So what happens when I increase the concentration of red particles? Are there more collisions in a low concentration or a high concentration? There are actually, and I don't know if the video capture rate is as smooth as I want to be, but you should be able to see that the red particles and the blue particles are bumping into each other more in the high concentration, right? So they have more of a chance to react. So if we go back to our note, okay, so the higher the concentration, means the faster the reaction, right? And the reason for that is that there are more collisions happening. Temperature. So we're going to go back to these gas particles, right? And I'm going to cool this mixture down. So as I cool this mixture down, you should see that now the particles are moving much more slowly, right? And when they're moving more slowly, they can't really get to the next particle to bump into it, right? So there are fewer collisions when molecules are going slowly. So when I reduce the temperature, right, the particles go more slowly and there are fewer collisions. When I raise the temperature, the molecules start moving faster. So you can see the temperature is increasing here in the thermometer. And as it increases, the molecules start going more quickly. And they will bump into each other more as they start moving faster. So the more collisions, the more opportunity that these molecules have to react with one another. Okay, and now they're bumping into each other quite a lot, right? Because now they're going quite a bit faster. Okay. So the higher the temperature, the faster the reaction. Okay, and this is because the molecules go faster and then they make more collisions with one another. And the last thing is the hardest to understand, the chemical nature of the reactants. The chemical nature of the reactant. So let's talk about this. So if you have for example, gas particles, they can mix freely. Right? So if you add two gases to a container, they collide quite a lot. But solids, they don't really move. So often our chemical reactions that involve solids will take longer to happen than gases. Right? So when we talk about the chemical nature of the reactants, it's what about the particles allows them to collide. Also bigger particles don't react as quickly as smaller particles. So we should add that. So particles, they have to collide. In the right way. Right, so for the reaction to happen, the particles have to collide in the right orientation. And smaller particles, because there's less of them, they're more likely, the atoms that react with each other are more likely to collide. So if you have a very big molecule, it will often react more slowly than if you have very small molecules, just because it's harder to get the right parts of each molecule to line up. Wonder if I can find. Wonder if I can find a video or a picture.
This is MSJ Cam. In this video, I'll be looking at collision theory. Collision. Note that in both these...
Okay. So here we have two chemicals, and these chemicals can react. But in this case, they did not react because although they collided, they didn't collide in the correct orientation, meaning not the right parts of the atoms collided, right? And so it can happen that two molecules can collide, and just they'll bounce off of each other because they're not in the right orientation to react. Okay, so these two molecules have to react. They have to be line up like top to bottom. So they have to be in the same orientation to react. So when they're both, let's say, when they both look like an 8, and they meet and they're sort of at the same angle, this collision has the right orientation, and then the molecules that end up together end up touching, right? So in this case, this is the correct orientation. So we have a chemical reaction. And the top, they didn't bump into each other with the correct orientation, and there's no chemical reaction, right? So molecules bump into each other all the time, and they have to have sort of the right speed and the right orientation if the chemical reaction is going to happen. So bigger molecules have a harder time doing that with smaller molecules. And things like solids, they don't move as much as gas particles. So we're talking about the chemical nature of the reactants. All right, so we're gonna talk about rate law now. It says it is of interest to chemists to quantitatively know how the rate of reaction will change. So we have some qualitative reasons why a factor might be something might make a chemical reaction go faster or slower, right? These are qualitative because we describe them in words, but chemists are very precise. They want to know mathematically how the rate of a reaction will change. So they want to come up with a rate law, which will determine, we can plug some numbers into it, and it will determine how fast a reaction will go. So that's why it says it is of interest to chemists to quantitatively, right? That's a number. Know how the rate of a reaction will change when a factor is altered. Okay. In other words, increasing the concentration will increase the rate, but by how much? Okay, that's where rate law comes in. So we know these 5 things will increase or decrease the rate of the reaction, but we need to know by how much. It is logical to presume that increasing the concentration of a substance will increase the rate of a reaction, but how do we calculate the relationship between concentration and rate? We would have to do some empirical experimentation, right? So we would have to determine this by experiment. So we have, this is a chemical reaction, and we have, normally we have the A and the B, where the A and the B are, we have coefficients, we have numbers, okay? And we have chemicals, which are X and Y. So it says the initial rate R, so initial means the starting rate. So the rate of a chemical reaction will change over time. As reactants become products, right, their concentration, the amount of reactant molecules that are left to smack into each other is going to decrease, right? So reactions don't happen at a steady rate. They start very quickly and then they slow down over time. Okay, so we're just looking at the initial rate, meaning how fast they start off, so we can compare chemical reactions. So the initial rate R is proportional to the initial concentration of the reactants. What does that mean? It means that the more concentrated the reactants are at the beginning, the faster the chemical reaction is going to go. So this word proportionality, right? This is where we compare amounts, right? The proportion. So we use the Greek letter alpha, and we can say that the rate of reaction is proportional to the initial concentrations of the reactant. So instead of having an equation, we have this expression here, R alpha reactant, the concentration of the reactants. So what this means is if the concentration of the reactants goes up, the rate of reaction will also go up. And if the concentration of the reactants goes down, R will go down. So the more constant, so that's what I mean about proportionality, right? If we have a lot of concentration of reactants, we have a very fast rate of reaction. Okay, so they're proportional. If you increase the concentration of reactants a little, you're going to get a little faster rate. If you change the concentration of the reactants a lot, you're going to have a lot faster rate. So what this tells us is that as the concentration of reactant increases, the rate will increase as well, but they are not necessarily equal to each other. So that's we can't use the equal sign, right? So it will go up by some factor. Maybe it'll go up by a factor of 2. Maybe it'll go up by a factor of 3. Okay, so it's proportional because it's not necessarily 1-to-1. Not necessarily 1-to-1. It could be a 1-to-2, 1-to-3, 1-to-4. However, they do increase with the same proportions. For example, if we double the initial concentration, then the rate doubles as well. However, if we multiply the reactant by a proportionality constant, then we can make this an equation. So the idea is the constant is the factor by which the rate increases. And each reaction actually has a different constant, right? You'll see K a lot if you take a lot of sciences. K means constant. So K means that there is some number that we can multiply the relationship by that makes everything work out mathematically. And German people came up with a lot of these constants, so we use the letter K instead of the letter C, because constant, if you spell it in German, starts with a K, right? So if you see a K as a part of a chemical, as a part of an equation in science, likely it's taking the place of a constant. Anyway, so the rate is equal to the concentration of reactants times some constant, times some factor that makes this an equation. So if we increase the concentration of reactants by 2, right, the rate can go up by 2. But it'll be 2 times some number. So what this, if we have more than one reactant, and we're likely to have more than one reactant, okay, we're going to have concentrations of multiple reactants, right? So here you can see the rate equals K, the constant, times the concentration of X, right? And that's one of our reactants, times concentration of Y, and Y is the other one. So what this tells us is we increase the initial concentration of X or Y, or both, the rate of reaction will increase. And this kind of makes more sense because, remember, if we have the higher concentration, we have more collisions. So if you have a higher concentration of X, right, that means more X molecules in the same space, and then they're more likely to collide, right? If you increase the concentration of Y, that means we have more Y particles in the same container, and then we're more likely to have collisions. If we increase them both, then the number of collisions will, of course, be even more. By how much? We have to find the proportionality constant for that reaction. However, not all reactants affect the rate of reaction equally. So increasing concentration of X by, say, 1 molar. So this is, when you see the capital M, it means moles per liter, right? So you might see 1.0 capital M, and that means 1.0 mole per liter. Mole per liter is our concentration units. So if we increase X by 1 mole per liter, it won't necessarily result in the same increase as increasing Y by 1 mole per liter. So therefore, we have to make a final change to our equation. Okay, so each reactant is going to have a corresponding exponent that shows us how much increasing the concentration will affect the overall rate. Okay, so we have to add exponents. The idea that different chemicals might have different effects on the rate is represented by these exponents. So we better read the very important point. In the rate law expression, the exponents m and n can only be determined through experimentation. So m and n are not related to the coefficients in a balanced chemical equation. They can only be determined by doing the reaction a few times and comparing. So we would take one of the reactants and we would hold it steady, right? It would have the same concentration over 2 or 3 reactions. And we would use higher and lower concentrations of Y. So we can see what happens when if you double the Y, do you double the rate of the reaction? Does it go up by 4? Does it go up by, 10? Okay, and then we would do the same thing with the concentration of X. So to measure the amount of change that X has, change in concentration of X has, we would keep Y the same, and we would do a couple trials where we increase and decrease only X. And then we can determine what the exponents are. Okay, so the molar coefficients to the reactants are not necessarily the same. So you can't just go by the chemical equation. Sometimes they are the same, but sometimes they're not the same. The exponents m and n are called the orders of reaction. They determine the extent to which the initial concentration of a reactant affects the rate. In other words, the greater the value of the order of the reaction, the greater the effect the concentration of that reactant will have on the rate of reaction. So, bigger exponent, bigger change in rate for that reactant. The sum of the order of reactions is called the overall order of the reaction. So to get the overall order of the reaction, add all of the exponents together. So in order to determine the orders of reaction for each reactant, or the overall order of reaction, we need to do some experiments. We need to do empirical data. So we need to run this reaction a few times. And in some trials, we keep X the same, and some trials we keep Y the same. Using known initial concentrations and initial rates of reaction under several conditions, the orders of each reaction can be determined. The key to analyzing a set of data is by comparing two trials which the concentration of only one reactant is varied. So if we want to study Y, we have to keep X the same, right? We have to control X. We got to make it a non-factor. So if we keep it the same in two trials, it's a non-factor. We know that however much the rate changed, it was only due to Y because X was the same. So for example, you say you have a chemical reaction with two reactants, we'll call them A and B. So we have A plus B equals some sort of products. You perform two trials wherein A is doubled but the concentration of B remains the same, right? So if B remains the same, we know that any increase in rate was not due to B. So mathematically, right, the change in the concentration between the two experiments, right, A is doubled in one of the experiments. So say the concentration was 3 moles per liter in one experiment and 6 moles per liter in the other experiment. 6 divided by 3 will give you 2, right? We can double it. It doesn't necessarily have to be 1 and 2. Just the concentration is double in one experiment for A. Okay, so it says, notice it doesn't matter what the actual concentrations of A in trial 1 and 2 are. What's important here is that we double. And then if the order of the reaction for A is 1, then we would expect the initial rate of reaction to be doubled as well. Okay, so if the difference between your concentrations is 2, and the difference between your rates is 2, we know that there is a 1-to-1 relationship. As the concentration of A doubles, the rate of the reaction doubles. Okay, and that means that it has a first degree power, right? So we would take the 2 to the 1, right? So we would take this exponent and we would add it to the rate law for A, right? We would put 1 as the exponent. Okay, but say, you're like, why not 2? I'll show you what happens when we have 2, okay? So say you doubled the concentration of A, but that quadrupled the rate of the reaction. So then we have the rate, instead of being doubled, will be 4 times, right? And 4 times is 2 to the exponent 2. Okay, so the exponent part would be whatever power gives you the rate change. So it should always be a power of 2. Okay, so your reaction can go twice as fast, right? And your exponent will be 2 to the 1, so it'll be 1. It can go 4 times as fast, in which case the exponent will be 2. It can go 8 times as fast, in which case the exponent will be 3. So you have to know your powers of 2 here, but like nothing above 3. So let's look at an example of how to come up with the rate law and come up with these exponents. So it says, consider the following data from trials of an experiment to measure the rate of reaction under different conditions with respect to the initial concentration. So they did so this is A plus 2B equals products, right? This is our chemical formula, okay? And we did an initial experiment where we had 1 mole of reactant A and 1 mole of 1 mole per liter of reactant A and 1 mole per liter of reactant B. And we found the rate of reaction was 1 mole per second. Boy, how convenient. I wish it would work that way in real life. It doesn't really. So in the next experiment, okay, we double A. So we made A more concentrated. In other words, when we were making the solution, we put more A powder in, right, to make the solution, but we kept B the same. Okay, so if we compare trial 1 and 2, okay, A doubled, B stayed the same. So we're studying what changing the concentration of A will do to the rate. And the rate doubled. Right? So this is a power of 1. Okay? So when the concentration, and when we do concentration, we do square brackets to show concentration. When the concentration of A doubled, R doubled, right? So the order or A is 1. We usually would say the order with respect to the concentration of A, but let's just say the order for A is 1. Okay, now we need to find an experiment where A stays the same and B changes. So if you look at trial 3, you can see A is the same between trial 1 and trial 3. And you can see that B, we changed the concentration of B by a factor of 3. But the rate went up by a factor of 9. Right? So when the concentration of B was tripled, the rate went up by a factor of 9. So in other words, okay, B for trial 3, so I'm going to say B3 divided by B1. So the concentration of B from trial 1, maybe we need to do this. We need to do the square brackets so we know it's a concentration. Okay, so the concentration from trial 3 and the concentration from trial 1, how does that relate to the rate of trial 3 divided by the rate of trial 1? Well, we know that the concentration in trial 3 was 3 times the concentration in trial 1, and we know that the rate went up 9 times. So how do these compare? compare exponentially. Okay, so the rate changed. Right, concentration changed by a factor of 3, and the rate changed by 3 squared. Right, so the order of reaction, or B, is 2. If we had to put an exponent on B to make the concentration difference and the rate difference the same, we would put the exponent 2. That's why we say the order of reaction for B is 2. So it says write the completed rate law for the reaction and state the overall order of reaction. So the rate law is always order of reaction is always R equals, the rate equals, some constant times the concentration of A times the concentration of B. And A and B have their own exponents. Okay, so I'm going to move that up. The exponent for A is 1 because when we increase the concentration by doubling it, we increase the rate of reaction by doubling it. So it's a 1-to-1 relationship. The exponent, the order of reaction for B is 2 because when we tripled the reaction, it went up 9 times, right? And the relationship between 3 and 9 is 3 squared, right? So the exponent, right, that you have to add to make it make sense is 2. Now we can calculate the rate constant K. It's very, very easy. Okay, so we're just going to use one trial. Let's use trial 3. Okay, so the rate, which is 9, is equal to K times 1.00 to the power of 1, to exponent 1, right? Times 3.00, because that was concentration for B, to the exponent of 2. So we can rearrange this equation, right, to find K. So K is going to be equal to, right, to isolate K, we divide the things that are multiplied on the same side as K. So K is equal to 9.00 moles per liter second. Divided by, have fun trying to draw this line. Nope, didn't work. One mole per liter times 3 moles per liter squared. Okay, so we're gonna have 9 on the top, and 1 times 3 squared, we're gonna have 9 on the bottom. So our K is equal to 1, right? But what are the units of K? Okay, so we have a mole per liter on the top. Which will cancel out with this mole per liter on the bottom. Okay, because the S came after the per sign, after the slash, this is in the denominator. Okay, this mole, so there are 2 moles because we have the moles and it's to the power of 2, right? So there are 2 moles on the bottom in the denominator and this is a sort of an annoying thing to think about, but if something is in the numerator but it's on the bottom of the fraction, this is a denominator. And if something is in the denominator of a denominator, it is a numerator. Okay, so this thing has the units of liter squared over mole squared times second. I hope that makes sense. Let me know, give me an email if it does not make sense. And I'll find a video on how to determine the rate law constant for you. So it says calculate the initial rate of the product for trial 4. So now, okay, now that we know K, we can take any 2 concentrations of the 2 reactants, and we can find out how fast it goes, right? So we have our rate law. So the rate is equal to 1 times the concentration of A times the concentration of B squared. Oops. Squared, right? For this reaction only. Not for all reactions, just for this one. So the rate is equal to the concentration of A in this case is 4. And the concentration of B is 2. So the rate of this, so 2 squared is 4. 4 times 4 is 16. So if you quadruple A and you double B, your rate is going to go up 16 times. Okay, so before even doing this trial, we would know that if we quadruple A and double B, we're going to get 16 moles per liter second. We have some practice problems, and I'm just going to do them with you now. If you want, you can pause the video, of course, do the questions on your own and like watch for the answers, or fast forward through the answers if you feel confident with this. So the question is, what is the difference between an order of reaction and the overall order of reaction? So an order of reaction is the exponent for one reactant. And the overall order of reaction is all exponents or all reactants added. Almost made that fit. Okay, so let's talk about this. We'll go back. Okay, so in the previous question, A had the exponent 1. So 1 is an order of reaction, an order of this reaction. Okay, it's the one that pertains to A. B had an exponent 2. That is also an order of reaction. That's an order of reaction with respect to B. But the overall order of reaction, which is a part of this, and I forgot to do it. Okay, overall, the order is 3. So we need to read the whole questions. Overall order is just, we're going to add the exponents. So this is an order 3 reaction. So a little addendum to question 2. Right, we just add the exponents. Okay. So the overall order of a reaction is all exponents for all reactants added. A series of experiments is performed on the following system. So we have 2 fictional reactants, A and B. Oh, sorry, no, I take it back. 3 reactants, A, B, and C. And they make 2 products, D and E. When the initial concentration of A is doubled, the rate increases by a factor of 4. When the initial concentration of B is doubled, the rate of reaction is doubled. When the initial concentration of C is doubled, there is no change in the rate of reaction. What is the order of reaction with respect to each reactant? So this is saying 2 to what exponent will give me 4? 2 to what exponent? So we'll change the exponent from x to y because these are different. They're different reactants. So one of the things with science is you got to try, if the numbers aren't necessarily going to be the same, you got to give them different letters. Okay. 2 to the y is equal to 2. And here we have 2 to the z is equal to, it says there's no change in the rate of the reaction. And that doesn't mean that it's 0. It's actually 1. Right? So the rate of the reaction before was, let's say, 3 moles per liter second. And then you changed C and it was still 3 moles per liter second. So the idea is you multiplied it by 1. Okay, so 2 to what power gives me 4? 2 squared, right? So what is the order of the reaction? Okay, so for A, it's 2, right? Because 2 squared gives me 4. For B, it's 1, because 2 to the power of 1 gives me 2. And for C, it's actually 0, right? So 2 to 0 gives me 1. 2 to the power of 0 gives me 1. If you have no experience with exponents and exponential equations, punch that into your calculator. Punch 2 to the 0 in your calculator and you should get a 1, right? It even works with 3, 4, 5. 3 to the power of 0 is 1. 4 to the power of 0 is 1. 5 to the power of 0 is 1. Okay, so it says write the rate law for the reaction. So the rate law starts with R equals, and then there's some value of K. And then it will be constant times the concentration of A squared times the concentration of B. And C has no effect, so we don't need to even write it. We can write just B, or we can write B to the 1, right? In chemistry, we don't usually like writing the number 1, so a lot of times you won't even see the exponent on B, okay? And a lot of times you won't see C even at all, because again, it has no effect on the rate of reaction, so it doesn't need to be involved in our rate law. The decomposition of SO2Cl2 occurs as follows. SO2Cl2. Ooh, don't know how do I name that one? So anyway, there's so there's one reactant and there are two products. The reaction is known to be first order with respect to SO2Cl2. Write the rate law for this reaction. So first order, right? That means exponent 1. So the rate law, R equals K times the concentration of SO2 Cl2, right? We're done with this AB business to the exponent of 1. Okay, if the initial rate of reaction is 3.5 times 10 to the negative 3, when the initial concentration of SO2Cl2 is 0.25 moles per liter, what is the initial rate of reaction? The initial rate of reaction would be if the concentration of SO2Cl2 were increased to 0.5 moles per liter. So we know that we doubled the concentration. And we know, therefore, that the concentration, the rate, okay, so we need to know this new rate. To the power of 1, this should also double. We don't even need to the power of 1. Okay, so maybe it's more appropriate to put the 2 to the 1 here, like that. Okay, so how do we find x? This is division. The 3.5 times 10 to the negative 3 is divided on this side, so it'll be multiplied on the other side. So x is equal to 2 times 3.5 times 10 to the negative 3, which is 7.0 times 10 to the negative 3. Okay, right. I just doubled the first number. If you double the first number and it doesn't go over 10, you keep the significant digits, the scientific notation, as is. And if not, well, we'll learn about that when we run into it. It says calculate K at a certain temperature T1. So the K actually will change at different temperatures. Usually if you have, if you look it up in a reference book, it's at room temperature, which is scientifically 25 degrees Celsius, right? It's not room temperature in science is 25 degrees Celsius. Some of you might say, I would never live at 25 degrees Celsius because that's too hot. Some of you would say, I would never live at 25 degrees Celsius because that's too cold. Scientific, we had to come up with consensus in science, so we said 25. Calculate K at a certain temperature if the rate is 2.4 times 10 to the negative 7 moles per liter when the concentration of NH4 plus. Oh, sorry, we have a new reaction. So the reaction where the rate law is this. So the rate law shows the order of reactants to be 1 and 1. But it doesn't show what K is. Okay, so it says calculate the K at a certain temperature if the rate of reaction is 2.4 times 10 to the negative 7 moles when the concentration of ammonium is 2 moles per liter and the concentration of NO2 minus is 5 moles. 5 times 10 to 3 moles. I'm going to need some more space to do this one. Can I? Here, this is what I'm going to do. So I'm going to open a Word document. Like so. Oh, here it is. I'm going to go into my Word. No, this is thermochemistry. We need not thermochemistry. Or close thermochemistry because we're, well, save. We'll do it out later. Okay. So we have a new, do new. Nope. So back. And we will unhighlight this. And we will take a screenshot. Okay. So, and we're going to zoom in. Don't worry. I know the writing is small. There you go. So it says for a reaction where the rate law is that, calculate K at a certain temperature if the rate of the reaction. So they're giving us R, right? It tells us the rate of reaction, right? The rate of reaction is R. Sorry. Okay, so they're giving us, this is basically R. And they're giving us NH4 and they're giving us NO2, right? And they're giving us the whole rate law already. So they're giving us the entire formula, K, concentration of NH4 plus, and the concentration of NO2 minus. Right, and there are no exponents there, which means it's 1 and 1. The order of reaction for ammonium, NH4 plus is 1. The order of reaction for NO2 minus is 1. And then they're giving us basically all of the numbers except for K, right? So the rate of reaction is 2.4 times 10 to the negative 7 moles per liter second. And that's equal to K times 0.200 mole per liter. And times 5.00 times 10 to the negative 3 moles per liter, right? Remember, if you see the capital M, that means moles per liter. Okay, so it's pretty easy to isolate this, right? We're going to bring these two numbers that are multiplied by K over to the other side, right? Both of these are multiplication. So when I bring them over to the other side, it's going to be division. So 2.40 times 10 to the negative 7 mole per liter second. Okay, divided by. And if you're pretty good at math and you wish to bypass this step, the second step here, you can. Okay, right? If you can kind of look at the equation and go, okay, if I isolate K, right? If I isolate K, I'm gonna have to divide by this guy and this guy, right? That's fine. But I'm doing it the long way because not everybody is always there. So we have to do we got to figure out the units too. This mole per liter in the numerator is going to cancel out with this moles per liter in the denominator. This S is after the slash. So this guy is going to go, this is going to be the denominator of our K. And this part is the numerator of a denominator. So that's a denominator. And this is the denominator of a denominator. So that's going to be a numerator. So let's do the math part. What did I do with my calculator? Oh, okay. So I do 2.4 times 10 to the negative 7. 2.4 times 10 to the negative 7. Actually, I have a calculator on my computer. Maybe I can show you how I do this on a calculator. So keep in mind that on the exam, you're going to actually need to bring, you can't use your phone. Okay, here's a scientific calculator. So I can go 2.40 times. Actually, I have a better idea. I'm going to clear this. Sorry. 2.4. If you have this EXP button on your calculator, it's not usually at the top of calculators. It's usually somewhere close to your equals key. If you have this exponent calculator, so this one is negative 7. There we go. This is a fast way to do 2.4 times 10. So the E stands for times 10 to the power of negative 7, right? So if I put the equal sign, this is the same as 2.4 times 10 to the negative 7. Basically, if you take 2.4 and you move the decimal place 7 to the right, 1, 2, 3, 4, 5, 6, 7, right? It ends up where the decimal place is here. Again, if scientific notation is confusing to you, please let me know. I'll send you some stuff. Okay. So that divided by 0.200. And then another divided by, and this one is 5 times 10 to the negative 3. So 5.00. The EXP is times 10 to the negative 3. So 3, but make it negative. There we go. Okay. And then so I get 0.00024. So K is equal to 0.00024. Let's double check the calculator. I always write too many zeros. Okay. Yes. 0.00024. And then the units would be, okay, so liters is in our numerator. Liters per mole second or second mole. Usually second is the last thing, mole times second. So liter is in the numerator, mole and second is in the denominator. You probably should turn that into scientific notation. So to get to have the decimal after the first non-zero digit, we have to move it 4 times. So K is equal to 2.4 times 10 to the negative 4 liters. Liters per mole second. Okay, let's go back to our this thing and oh, there's no answers here. No. Well, that's the answer. Interesting. Do I not have, don't have answers on this one? Well, I guess that means I have to improve some things, doesn't it? Okay. Then we have question 5. What would happen to the, okay, what would happen to the value of the rate constant K if the following were to happen? The temperature of the system was increased. Okay, so we can say as the temperature increased, right? So this is how we would say it in science. As T goes up, okay, R goes up, right? Because they're proportional. The concentration of a reactant increased as C goes up. C can stand for concentration. R goes up. A catalyst was added, then R goes up. R always goes up. Doesn't matter even how much, just R goes up. Last question. Okay, so we're gonna need to do a little screenshot here and move this over to, so I have the space, I think. So when aqueous bromate bisulfate ions react to produce bromine, the overall equation is that. Well, that didn't work. Okay, let's see if I can get the cursor down here. Oh, I see. Hold on 1 second. There you go. Okay. So we have this reaction. It's an ugly looking reaction, a lot of reactants, a lot of products. Okay. This first guy, this is bromate. And this one here is bisulfite. And then we have products, right? We have bromine gas, sulfate ions, water, and hydrogen ions. It says, consider the following data from the set of trials of an experiment to measure the rate of reaction under different conditions, right? So they basically, because bromine is the only gas, it's easiest to measure the rate of this equation by looking at the amount of bromine gas. So this would be a gas collection experiment. Right, we know that's one of the ways that they measure the rate of a reaction is by collecting gas, if gas is one of the products. So we have 3 trials of this, and we're looking at both of the reactants. We have bromate and we have bisulfate. So you'll notice that in trials 1 and 2, the initial concentration of bromate changes, but the initial concentration of bisulfate stays the same. So we can use those 2 trials. I'm just going to make this a little bit smaller. Okay, for A, for bromate, which is BrO3 minus. Okay, we're going to use trial 1 and trial 2. So the concentration of bromate in trial 1 is higher, right? And you can do it the other way, but if you do whichever trial is higher on top, you're going to get probably a whole number, and if you do it the other way around, you're going to probably get a fraction. And I know how much most people hate fractions, even though they've done nothing to you. So we're going to find the proportion of the concentrations. And we are going to compare that, okay, to the rate portion of the rates. Actually, I did the brackets around the wrong part. Okay, so the proportion of the concentrations to some exponent will be will equal the proportion of the rates, right? So we're finding the order of bromate, and that's kind of how you do it in the equation method. Okay, so now we fill in numbers. So we have 4.0 millimoles per liter. Right, that's 1,000th of a mole over 2 millimoles per liter. And then we compare the rates. So rate 1 is 1.60 millimoles per liter second. And 0.80 millimoles per liter second. So we can see here 4 divided by 2, right? The concentration doubled. And the rate doubled as well. Right, so 2 to what exponent gives us 2? The order with respect to bromate is 1. Right, so the order for bromate is 1. Okay, so I can keep the rest of the question visible. I am going to erase what I've just done. So if you need this still, let me just pull it everything into frame. You can pause right now so you can finish copying it down. Okay. Okay. So I assume that you have it copied down now. And then we're going to do the same thing, but there's gotta be a faster way to do this. Delete. There we go. Okay, so we're gonna do the same thing for bisulfite. So bisulfite, which is HSO3 minus. So bisulfite, we're going to need 2 trials where bromate is the same. So that's trials 2 and 3. So we're going to use trials 2 and 3, right? You always have to choose your trial so that the other thing has no effect, right? So you want the concentrations to be the same. Okay, of the other thing, not the thing that you're trying to find, the other thing. So when we do the concentration, so the concentration of HSO3 in trial, what trial should we use as a numerator? 6 is higher than 3, so we're going to use trial 2 over the concentration of bisulfite sulfite in trial 3 to some exponent is equal to the rate in trial 2 over the rate in trial 3. So just make sure that the trial that you're using in the numerator is the same, and the trial that you're using in the denominator is the same. And then we're going to go, so the concentration, so this is 6.0 millimoles per liter, and this is 3.0 millimoles per liter. To some exponent, we can't use x, so we used x last time. So we're gonna use y. Oh, I put x in the formula. Well, that's not good. We already have an x. We need a y. Okay. And then we have the rate in trial 2 is 0.80 millimole per liter. And in trial 3 is 0.20 millimoles per liter. Come on, pen. There we go. Right. So 6 divided by 3 gives us 2. So 2, really, just let me right here. 2 to some exponent gives me 0.8 divided by 0.2 is 4. Right. So y here has to be 2. 2 squared is 4. So for bisulfite, it's 2. Okay, so next question. Again, I'm gonna erase this so we can keep the question on at the same time. So pause the screen if you need to write things down. And I will move on. Delete. Okay, it says write the complete rate law for this reaction and state the overall order of reaction. So rate law, rate is equal to some constant times the concentration of bromate to the exponent 1 times the concentration of bisulfite to the exponent 2. That was easy, right? You just add the orders. Okay, and the overall order right? We just add the exponents. 1 plus 2 equals 3. So that was easy. Calculate the rate constant K. So K, right? If we isolate K, it's going to be the rate divided by the concentration of bromate to the power of 1. And the concentration of bisulfite, the power of 2. So we can pick any trial we want. And we'll do trial 3. Numbers look nice and low. So K is equal to so the rate in trial 3 is 0.20 millimoles per liter seconds divided by concentration of bromate is 2.0 millimoles per liter. And concentration of bisulfite is 3.0 millimoles per liter. Okay. So let's look at units. Let's get rid of some units. Okay, so we have a millimole per liter on the top and a millimole per liter on the bottom. And those things are cancel out and not be a part of our final product or our final K units for K. Okay. We have millimoles and liters on the bottom. This is going to be in the denominator. This is going to be in the numerator. The S is going to be in the denominator. So we 0.2 calculator. Okay. Another calculator pro tip. Okay. If you have 0.20, you really only need to type in 0.2 into your calculator. So 0.2 divided by, this is 2.0. We can just say divided by 2. And then the last one is 3.0. We can just say divided by 3. So that gives me 0.033. 3. And then, okay, so let's work on our units. So we have liters squared, right? Because we have to apply this exponent 2 to the liters because it's outside the bracket with liters. So that's the only thing in the numerator. And then we have millimole squared in the denominator. And seconds in the denominator. And there we go. So that is the rate constant K. I'm going to write that down. K is equal to 0.033 liters squared per millimole squared times second. If you want to put this in scientific notation, it would be 3.3 times 10 to the negative 2. All right. So the very last question. it says calculate the initial rate production for product 4. So I'm going to get rid of these calculations so we can have everything on screen at the same time. Delete. Calculate the initial rate of production for trial 4. So we know, so we're just going to use the rate law. Rate is equal to K times the concentration of bromate to the power of 1 times the concentration of bisulfate to the exponent 2. And then we're going to fill everything in. So K is 0.033. And the concentration of bromate for trial 4 is 3.0. Oh, we should use units, because it should work out to millimoles per liter second. Interesting, it's not letting me erase. Oh, now. Nope, just not letting me erase. All right, okay. That's fine. We won't use units. We'll be rebels. So we have 3.0 as the concentration of bromate, and 4.0 times as the concentration of bisulfite. You gotta square it. So 0.033 times 3 times 4 squared equals 1.584. So the rate is 1.584 millimoles per liter second. Okay, so your rate should always match whatever the units are on the top of the rate column, because that's what rate is measured in. That's it for the homework today, right? Am I right? Is it over? Yes. So have a good day, and we will see you tomorrow.